Now, Professor Qingmin Li is going to use the word. Professor Qingmin Li is part of the working group C4 208 and 330 and member of the 3 IET. He is part of the editor board of several international magazines. He graduated at the Tsinghua University in Beijing, China, where he graduated in engineering in 1991, master's in 94, and his PhD in 99 in electrical engineering. Currently, he is a full professor at the College of Electronics and Electric University at the China University at NCEPU. He worked at the Tsinghua University as assistant professor in 96 and worked as postdoctoral student at the Liverpool and Strathclyde universities. In 2000, he worked as a visiting professor at the State University of Arizona. His area of interest includes high tension, gas, discharges and gas, and physics of arcs, monitoring and diagnosis of faults in power equipment, amongst others. The word's yours.
Yeah. Okay, many thanks to Professor Maria Cristina for your introduction, and good afternoon to everyone. Firstly, I would say it's great to have so many researchers all over the world come here to join the seminar. It's indeed gave me a great boost for my research to continue in the area of half wavelength technology. And then I think it's thanks to Maria to organize this academic seminar and give me the precious chance to present what we have done in China. And actually, in China, there are quite a few researchers working in this area. Here just to report what I have done. Especially on secondary arc physics. Yeah, it's quite a little more emphasis on physical aspects. As compared to the the previous presentations. Okay, now comes my report as experimental study on secondary arc physics with half wavelength power transmission lines. Then the contents compose the introduction and experimental study and dynamic modeling of the secondary arcs and the suppressing methodology for secondary arcs, and then conclusion. Firstly, I would give a very brief introduction to the background. Some background with China. The half wavelength transmission lines, the concept in China. As everybody knows, the power sources and the consumption of power in the power sector, is unevenly distributed in China. The power sources is normally based in West China, and the consumption is mainly based in East China. Then it's need a long distance for the power transmission. Then comes the requirement for people to consider half wavelength transmission lines. And also, from the future point of view, we have some potentials to transport power, powers from, internationally, for example, from Mongolia or from Russia. Okay, so it's the very brief introduction to the background for the requirement of half wavelength transmission technology. Here give you some ideas what happens in China with half wavelength transmission technology. In 1993, half wavelength application draw close attention in the power sector of China. Yeah, especially in the universities and the EPI of China. And in 2008, further ideas on half wavelength was put forward by as academician of Chinese Academy of Science of Engineering, Professor Zheng Jianchao. Yeah, he led the research. And in 2009, the State Grid of China set up the first strategic research topics on half-wavelength technology. Then, fortunately, I got a project with State Grid on secondary arcs. And in 2011, the Chinese Society of Electrical Engineering shortlisted half-wavelength technology in the specialized area for future development in the power sector in China. So that's the brief introduction, to the concept that comes with in China and with half-wavelength transmission. I think the previous presenters have given the advantages of the half-wavelength transmission. Just mentioned here, it's the advantages. It's without the reactive power compensation and extremely good voltage stability and large transmission capacity, and excellent features in economy, and high reliability, and etc. But they still have some challenges to realize this technology into reality. I just gave some, something and for your reference. And first one, fault-induced or switching voltages must be very careful to pay more attention in the future research. Okay, and then comes power dispatch along the transmission line. That's what the topic Professor Lei Qi from, as my colleague gave in this morning, okay? The power dispatch means power extraction from the lines. And the power relay and protection scheme, I think Professor Maria Cristina has done a lot of work on these schemes. And then comes the first one, secondary arc extinction and auto-reclusion. That's what I focus on, because second arc extinction is very, it's very close with the auto-reclusion strategy, because for half wavelength transmission line, it's automatically compensated by itself. There's no four-legged inductors to limit the secondary current. So we must consider, what the second arc will be and how to extinguish in a quick style. So that's we have done experiment to get the physical, behaviors and to form the physical basis. That means to set up a reclusion scheme. Generally, second arc is following the first primary arc. It's a short circuit arc, discharge. Then comes second arc. And, it's generated by normally followed by following the single phase grounding fault. When then the short circuit arc discharge happens, then on both ends the fault phase switched off. Then this figure gives you the short circuit arc. Then the next figure is secondary arc. Next, we have done on-site experiments with the UHV transmission line. It's not with half-wavelength transmission line. It's just the UHV transmission lines in China. We have done on-site experiments to do the short-circuit test with the arc discharge, recorded by video systems. As you know, there are several potential impacts of the second arcs. First, I think the very close relations with the single-phase reclusion failure may cause the reclusion failure, and also may endanger power equipment. As I have said, there may be some unique secondary arc characteristics we are not known. So that's why we try to carry out experiments, and also the factors due to extremely long length of the transmission lines and the complicated coupling between transmission line phases, yeah, and the existence of the series compensation network, may be called adjusting network or something else, yeah. Now this figure is based on a very simple simulation. Then you can see along the lines is a large secondary arc current, maybe, for example, it's maybe over 1,000 amperes. Yeah, this is a simple simulation. So that's it to say we must take special suppression measures, yeah, to limit the current. Otherwise, the arc will not be extinguished. And also, you know, the short circuit current is very large. It will show some impacts on the secondary arcs, and the maximum is not yet clear enough at the moment. And also, unique electrostatic induction component should be considered, yeah, as compared with the conventional UHV transmission lines. The half wavelength, wavelength transmission lines, we must consider these components for the design of the recloser. And also electromagnetic transient interaction process with the power system and with the arcing characteristics. When we do simulation, we normally forget or ignore the arc characteristics, yeah? But, it does show impact on the, on the transient behaviors. So that's why we do experiments. And also, the traditional secondary arc suppression method is no longer, applicable. Why? Because no it's no four-legged inductor. Yeah, that's the case. So we must consider, a new methodologies to suppress the secondary arcs. Yeah, that's the target. That's the purpose of our research. That means the unique secondary arc behaviors present a challenge for developing half-wavelength transmission technology. In that case, further study on secondary arcs is necessary with a view to clarifying the physical mechanism as well as proposing effective suppressing measures. Okay, now comes what we have done an experimental study on the secondary arc physics. Yeah, there is no practical project at the moment so far all over the world. We cannot do on-site experiments. We just do experiments in our high voltage lab. So we must base on some equivalent transformer for the real three-phase transmission lines. They use, this figure is a single-phase circuit that we based on to establish a test rig. Yeah. In that case, the single-phase earth fault can be simplified as a single-phase topology, as shown in this figure. Yeah, it's the red circle. Yeah. That's based on the simplification, we have established a test rig. Yeah, we call the test platform. It's mainly composed of test circuit together with corresponding measurement system, including we are using a 10 kilowatts AC power supply to do the short circuit test directly with large current. Okay, and also we use copper electrodes, high voltage insulators, and fuses to ignite the arc discharge. Arc discharge means the primary and the secondary. Yeah, and the arc trajectories are recorded with a high-speed video camera. Yeah, that's the test site in our high voltage lab. Here gives some experimental instruments and equipments. I don't want to to name them one by one, so wasting time. Yeah. Now here is the side pictures for the experiments that we have used. Yeah. Here is give you some images of short circuit you may call primary arc, short circuit arc, and the secondary arc. And the left one is short arc discharge, and then on the right is secondary arc discharge. Yeah. The short arc current is bigger than the secondary arc, and the arc move speed is faster. And the movement direction of each part is different and severely changeable. The second arc deflection or deformation occurs continuously. The arc root has a polarity impact and has the obvious tendency to move up. It's moving back and forth at one location. Let's see the overview, is in the current voltage waveforms of the short arc and second arc. You can see some difference between them. Because the second arc, the current is very low compared with the short circuit arc. Yeah, and the waveform shows slight changes. Yeah, as the voltage waveform, the second arc is similar to an saddle. Yeah, yeah. And due to the electric arc thermal inertia, the current peak often lags behind the voltage peak for the second arc. And these figures give the harmonic characteristics that just for your reference and doesn't carry any emphasis. Here I will show you some physics, typical motion characteristics of second arc. The first is the motion of the cathode arc root. This is the overall. Then the motion characteristics of the cathode arc root, the anode arc root, and the arc column are significantly different. Arc root motions are with polarity effect. The cathode arc root is composed of electrons, positive ions, metal ions, and ion molecules, wherein the electron beams emitted from electrode is dominant, perpendicular to the cathode surface. The cathodic arc root is difficult to move. The length is changing with the current. And the anode arc root is mainly similar. The motion direction of the ions is opposite to the electrons. There is a displacement of the anode arc root during the combustion. Yeah. Then we pay more attention to arc column motions. It's quite complicated. It's in an open, because the arc burning in open air, the open environment is influenced by the external environment, such as the wind. Yeah, there's often a short circuit and some segment diminishing phenomena appears, easy to break down with the anode forming arc root jump phenomena. It shows upward motion trend. Yeah. This figure just give you examples because we have, recorded many pictures. Yeah. Now here is just the summary of the motion mechanism of the secondary arcs. Yeah. For the up one, yeah, the figure A. Yeah, this is the means this not exactly secondary arc. It's the primary arc, the short arc. Yeah. Also, as we found that the secondary arc column mainly experience a horizontal motion at the earlier stage. You can see the up image. Yeah. And in a lower image, it's in the second stage of the arc discharge development. Yeah. It's driven by the hot air convection. The arc column mainly performs a vertical motion. Yeah, vertical motion. Here is just to give a very basic explanation in physics, yeah, just to show the motion mechanism of the secondary arcs. Due to the difference in mass, the moving speed of the ions is much less than that of the electrons, and thereby the current inside the arc column plasma is mainly formed by the movement of the free electrons. That's shown in the figure. And during our experiments, we have discovered some, a special phenomenon we call the short circuit of the second arc during motion process. There are two kinds of short circuit phenomena of the second arcs. The short circuit phenomena typically happens during the motion process. It can be normally manifested in two aspects. One is short circuit between the arc column and the electrodes. The other one is short circuit between the arc sections themselves. Yeah. The upper one is for the short circuit between the arc column and the electrodes, and the downward one is for short circuit between the arc sections itself. Now you can also see the short circuit phenomena from the waveforms of the current and the voltage. You can see the figure A is for short circuit between arc column. You can see it's a sharp downward of the waveforms when a short circuit happens between the arc column and the electrodes. And this also is true for the short circuit between arc sections themselves. It's the right figure, namely B. Yeah. Also, we have found an induced phenomenon of the cathode arc route. For arc discharge, you must pay very close attention to the arc. It's called arc route. Yeah, arc route. Electrodes, the phenomenon with the electrodes. Now here you can see there exist two cathode arc routes, and the spatial distance between the two is usually very short, and it renders random behavior. Yeah, that's what we have recorded in the experiments. And now I show you with some figures with the wind effects on the arc movement and the arc motions. It's also found that the second arc burning in the free space is more easy to be influenced by wind loads. The moving trajectories of the second arc and the stress of the wind forces are shown in the figure, and the wind direction is perpendicular to the arc channel with a typical wind speed of 1.5 meters per second. As we said, when we do experiments, we use the, fans to simulate the wind, yeah? Then we set the speed to this value, yeah. Here, the picture shows the wind in the same direction with arc motion. Even though without wind, the arc will move upward or outstretch, yeah, to the with the long, called arc length, yeah. If the wind in the same direction with arc motion, then what happens? It will accelerate the dissipation of the plasma in arc tract and enhancing the arc energy exchanger with the outside world. In that case, the speed up the arc extinction means the arcing time will become shorter, yeah? Yeah. And these pictures gives the case when the wind in the opposite direction with arc motion. Yeah. In this case, when the wind direction is opposite to the arc motion, the development of the arc will be inhibited. Means it will hamper. Yeah. At this moment, the arc burning time also significantly increased. It means the arcing time and become longer. Yeah, that's when the wind, the direction is opposite to the arc motion itself. As can be seen from the figure, there is arc root jumping phenomena, as we have found, and the action of wind and the thermal buoyancy. The arc column is stretched along the wind direction. Yeah. And here the figure is give you the relationship between the length of the second arc column and the arcing time. Yeah. It can be found that the total length of the second arc column increased slowly at the early stage of the arcing process, but it rises very steeply before the arc is nearly extinguished. It's a sharp, yeah, as a sharp rise, in the final stage. Okay, we have also done some, research, as experimental research with your series compensation, maybe you call adjusting network. Network is set in three cases. One is uncompensated, one is undercompensated, and the third one is overcompensated. Now with the same arc current, 15 amperes and double is 30 amperes for the two cases. And also we have set recovery voltage gradient, means when the arc discharge is extinguished, then will come the recovery voltage. It's the steepness, the gradient. Yeah. Here is the two pictures. Then we have concluded in the two pictures. One is for a second arc current with 15 amperes, and the right one is with 30 amperes. Then you can see the three cases. There's uncompensated, undercompensated, overcompensated. Yeah. Then you can see without compensation means without the congesting network. Then it gives the longest, extinction time of the all. Yeah. And in another way, you can see with different degrees of compensation, the difference is sensible. Yeah. Means if we use appropriate compensation, the arc extinction time can be greatly shortened. These figures give you the three cases, the test results with the currents and the voltage, the recovery, recovery voltage. Yeah, just give you, overview. Yeah. Now here, it's just a brief summary of this part. The motion of the anode arc root and the cathode arc root and the column is different. And short circuit and the induced phenomena often occur during the process. And the wind plays a very key role in, to influence the second arc physics. Yeah. And with different degrees of compensation, the extinction time may differ a lot. Yeah. Then I give you what we have done on the modeling of second arcs and try to compare the modeling with the experiments. Yeah. It's a cascaded chain model we have adopted for the second arcs with a mechanical model of a single current element. Yeah, I just gave you a concept. I have no time to explain in details here. Yeah. Due to time limit. Yeah. And the digital simulations of second arc motions is further carried out based on the dynamic model we have proposed above, with a view to characterizing the spatial movement and the evolving mechanism of second arcs and try to compare with the experimental research. Next simulation, we can consider thermal buoyancy. Yeah, as we just do a two-dimension simulation. It's not a 3D, it's a 2D simulation here. Yeah. Now you can find that. You can find that without thermal buoyancy or with thermal buoyancy, you can get different results. But for if you try to to simulate the real condition, you must consider the thermal buoyancy. Otherwise, you get maybe wrong results. And another factor we consider is the wind force. And in the dynamic modeling, we consider the wind force. Yeah. Then you can see, this is the simulated motion trails of the second arc under stress of wind load. As the wind load, it means in the direction opposite to the arc itself. And that you can show that you can see the dynamics of the arc. Then with time, then you can in a rough way you can see it's something similar with the experiments. Yeah, we can't say it's exactly to model the dynamics of the arc physics because actually it's too complicated. Yeah. But I use this simulation tool, we can guess or we can predict some physical behaviors of the secondary arcs, to help us to explain or elucidate the details of the secondary arcs. Yeah, that's the purpose. Okay. Then comes, why we have spent a lot of money and time to working on the secondary arcs. The purpose is try to develop ideal, auto-reclusive scheme for the protection of the half-wave transmission, transmission lines. So we have done some research on suppressing methodology, to limit the second arc, So the first one is, I think you are quite familiar if you are familiar with half-wave transmission technology. So it's called high-speed grounding switch. High-speed ground switch. Yeah, we have done some simulations and incorporating the second arc model. Yeah, so it's try to get accurate results. Yeah, yes, we can use different set of high-speed grounding switch. Then you can get different results. Yeah, you can see these two figures. The left one is second arc current, and the right one is recovery voltage when after the arc extinction. You can see different set of high-speed grounding switches. You get different results. In that case, means the high-speed the distribution of the high-speed grounding switches can be optimized. Yeah, then with a view to reduce the secondary arcs and reduce the arc reignition. Yeah. And the second one, I just gave you is a figure here. It's a novel method we have proposed. Yeah. And the paper has been published in, I think maybe you know, it's the journal, international journal, the European, the ETEP, European transactions. Yeah. As no method means that we just put impedance parallel to the line circuit breaker. Yeah. Because for the conventional transmission lines, normally a four-legged inductor is used, but now you have no four-legged inductors. Then we just present as a method is called impedance parallel to the line circuit breaker. It's mainly composed of resistor and with inductor in series. Yeah, it means that we'll inject you can see inductive currents to compensate the capacitive current. Yeah, this means then you can get a compensation then to reduce the second arc current. Yeah. Here some words explain how to operate the sequence, how to control the switch K1 and K0, just to switch in and switch out of the resistance, of the impedance. Yeah. With proper setting of the parallel impedance 0, yeah, the formed current by electromagnetic coupling from the healthy phases and the injected current from the faulty phase may possess equal amplitude, but with inverse phase angle. That's the the physics behind the scene means that you can to do the compensation completely. Yeah, as theoretically we can do the compensation 100%, but in fact maybe we cannot achieve this purpose. Yeah, okay. Next is with this approach, so as to accelerate extinction of the second arcs. Okay. Then finally, maybe my time has passed the limit. I give us conclusions in a quick style. Yeah, the second arcs of the half wavelength transmission lines is different from the ordinary transmission lines and need detailed study. Experiments are carried out focusing on the second arc physics, and unique motion characteristics are discovered in the experiments. And the dynamic modeling is adopted to study the motion mechanism of the second arcs, and it shows quite good coincidence with the experiments, but I still need further study. Now my students are working on this technique to develop a 3D modeling of the arcs. Yeah. And some suppressing methodologies for the secondary arc with high-speed grounding switches is proved to be effective, and a novel method based on impedance parallel to the line set breaker is proposed. Yeah. Okay, that's all for my presentation. Thank you very much.
Propose a new method to extinguish the arc through the connection of resistance in parallel to the circuit breaker. Depending on the location of the short circuit, this resistance does it have to be changed or regulated or tuned?
Certo? Take off your headsets or you'll be listening to the translation.
Okay.
Вы знаете, что да, для этой новой методологии, которую предлагаем, я бы сказал, что мы еще добавочные исследования, но это только схема.
Uma simulação teórica e para provar que seja efetiva, e sim,
comes our. If the circuit breaker you put different places, maybe the impedance not exactly resistance as the inductor, the inductive, yeah, impedance. Maybe will be changed the value, the amplitude, yeah. I agree with you, but it still need further, simulation or verification, yeah. Thank you.
Еще один вопрос. Вы предлагаете также шунтировать аварийную фазу в средней части линии. Так, предлагается шунтировать фазу аварийную в средней части линии.
Do you use English?
Пробовали ли вы шунтировать в нескольких точках линии?
Do you mean the simulation or something? No? 3D simulation?
Ну, естественно, при исследовании дуги в полуволне.
The translation not yet come. Yeah. I try to get your idea. Do you mean the 3D modeling? Do you mean the 3D modeling we have done, yes, sir?
When you say,
No.
Maybe. I haven't got.
I suppose that when you say is to include the resistor in several points along the line.
Yes.
He says resistor, but it would be your inductor. It would be inserted at several points along the line, or just in circuit breaker.
Shunting breaker.
Yeah.
Several points.
Sorry, I didn't catch your idea. For the high speed, I would say for the high speed grounding switch, we did do some simulations. If it's along the lines, yeah, there will be an optimal solution for suppressing the second arcs. Okay, and for the new method, we have not done yet. Have not yet done the simulations. Just put the circuit breaker on both ends. Yeah, at the moment. Okay. Thanks for your question.
Thank you, Professor Jin. My question is related with the electric field which is needed.
You are speaking English?
English,
okay.
Yeah. Yeah, my question is related with the electric field which is needed to break the gap. It's close to a streamer discharge 500 kilovolts meter, or is lower. This is related with that in this case we can have lower breakdown electric fields. Is it so, or?
Okay, that's a good question, I think. Yeah, when we do experiments, we cannot simulate everything of the real world. For half wave transmission lines, for example, it's not a half wave, maybe the UHV, okay, transmission lines. The arc length may be more than several meters long. Okay, for our research, we simulate the arc length means use the insulator. What we have used is just the 1.5 meters. Sometimes we use 1 meters long. Yeah, that's what we have used. That's due to the experimental limit. Yeah, and that's what in the conditions we have. We just try to make use of what we have. Yeah.
And the polarity you used was positive polarity or AC and
The test source is AC. Test source AC we use directly to make it's a direct a short circuit test. Means just connect to 10 kilowatts as test source with a large capacity transformer. Yeah. Yeah. When we do experiments, the consumers just around the lab will complain, because there's a short, it's the power quality issues will happen when we do experiments. Yeah.
I see. Yeah, and just the last question. The breakdown came in the positive polarity, I suppose, or
Say again, please.
in the breakdown appears.
The breakdown, yeah.
Appears in the positive polarity of the AC waveform or in the negative polarity? Just
Do you mean the breakdown the point on view?
in this experiment,
Yeah.
when you have breakdown, it appears in the positive polarity of the AC waveform.
Oh, it's random. Yeah, random. Both
Both polarities.
Both possible. Yeah.
Okay.
Yeah.
Thank you very much.
Okay, you're welcome. Will you use English or you? Okay.
When you extinguish, how do you extinguish the arc? When the arc, you said the arc, the extinguisher is you showed some tables with 15 amps, 30 amps, and then there was a time of extinction. How the arc extinguish?
Okay, I know your point. There's no limiting measures have been taken because it will. We just try to follow, what it will, what and how it will go, just to catch up the physical phenomena. Yeah, the arc will be extinguished by itself. Yeah, by itself. But it depends. The arcing time may be different because we set up different conditions. Yeah. For example, the parameter is different. The wind speed is different. Okay. Then you get different, experimental results. Then you can see, no special design for the suppressing methodologies for the tests.
Yes, for the test, because you were presenting the length was increasing at arc extinction. So
Okay. Because when the theoretically when the arc length approaches maximum, the means the power means the energy cannot withstand the arc plasma, then it will be extinguished by itself naturally. Yeah. Then you can see, if the current is big enough, if the current means the second arc current, maybe keep arcing there. Yeah, maybe. Yeah. Sometimes it need quite a long time for the arc to extinguish in the experiments. Yeah. Look here. I just ignored this table here. Sorry. Yeah, here. You can see when the second arc is below 120 amperes, here, then the second arc will be quickly extinguished. Yeah, but if the second arc current rise to 240 amperes, the arcing time will become much longer. Yeah, that's the point. Yeah.
okay.
Then in the experiments we cannot, model everything. It's just to try to get the tendency of the arcing time.
Okay.
Yeah.
These arcs were 1 meter long.
Yeah, it's 1 meter long and 1.5 meter long. It's depending on how long the insulator is. Yeah. Okay.
Well, it's more than one question, okay?
Yeah.
First,
You're
about the
welcome.
wind. We have here a research about the secondary arc modeling, but it's exactly the opposite of what we have concerning the site. Because we have an experimental line of 500 kV, out of the laboratory. We have only the real conditions, see? So, for example, the wind, we have 3 components at Rio, not only one direction, see?
Yeah.
And we measure this. We make the arcs, and then we measure the wind at the same time. So we have 1 second to study the phenomenon, and that's what with what we work. So about the wind, maybe you should think on, I don't know, varying this kind of wind you have inside the laboratory, because it does not really represent what we see at the field, see? Because it makes difference, the wind is very important to change the arc.
Yeah.
And it's very interesting to this kind of exchange, because you see from one point we have other points, and it's very good. And we can say, as you said about the thermal inertia and so on, and have the electric too, that they combine themselves, but it's very hard to model the arc, considering just we say one time constant. You see. We need more than one just because of all this phenomenon. So maybe you should take care of these things.
Yeah.
And what about the high-speed grounding switch? We are talking about a very large line.
Do you mean the high-speed grounding switch?
Yeah, high-speed grounding switch. That's it. So maybe the requirements is not so usual as the technology to deal with the capacitance and other things that we feel the results with that when we are working with a half wavelength line, see? So it's not an ordinary high-speed grounding. So maybe we should use more, we have to accomplish more than one technology to make use of this kind of things.
Yeah, okay. Thank you very much for your not exact question. I think you set up the question that answered for me as well. Yeah, just give me some good advice for me to carry further my research. I think you have done excellent research. It's quite similar to what we have done, because you have used higher voltage on-site test. I think with the transmission lines. Yeah, and the situations are quite random. It's the natural wind. And so what we have used in the lab, we must control the wind in one direction. It's difficult to control the wind from this way and this way. Yeah, but for environmental test, on-site test, you can the wind comes naturally from the environmental situations. That's a good result. And for the high-speed grounding switch. We just, we never done tests, just doing some research on simulation. Yeah, we can tell you some, useful results. For example, how to be a guide for the practical design, how to set up the switch along the lines to get a minimum sector arc current. That's the purpose. Okay, maybe we can communicate after the seminar. Okay. Yeah. Thank you very much.
Bom, acho que nós podemos encerrar e vamos para o intervalo e voltamos, que o nosso horário já está completamente fora. Obrigada.
Thank you.你去把那个，你去把关键下去啊。